Hello! In the previous video we introduced the relativistic momentum, a four-vector that generalizes Newtonian linear momentum and is conserved under Lorentz transformations. Now let's spend some time understanding its implications. The relativistic momentum was built based upon another four-vector, the spacetime displacement ds. Remember, ds is a four-vector where each component is the displacement in each one of the four dimensions: c, dt, dx, dy, and dz. We define this four momentum as the mass times the derivative of the spacetime displacement with respect to proper time. It has four components, a temporal one and three spatial ones. It is a four-dimensional vector that is tangent to the trajectory in space-time of the particle. All four dimensions are treated equally on the same footing. We found the equations of transformation of the four momentum. These equations, written properly, have an impressive similarity with the transformations of time and space. Let's
take a good, long look at it.
Here you have side by side the equations of transformation of the four components of the displacement four-vector and the equations of transformation of the four components of relativistic momentum. They just look the same. They transform in the same manner. The symmetry is much more clear if we write it in relativistic units. Those where, instead of writing the velocity, we write beta, and therefore the speed of light is 1. This is really beautiful. We can see here how space and time are just really different components of the same thing, of the same structure. They are intertwined. As in Newtonian physics, momentum conservation implies that all four components are to be conserved in a collision. The three spatial components reduce to Newtonian linear momentum for small velocities, and the conservation of four momentum reduces to the conservation of linear momentum. This conservation of four momentum has been tested uncounted times in particle accelerators, where thousands of collisions take place. All of them satisfy this conservation law. But this four momentum has a new term with respect to Newtonian momentum. What is it? What does it mean? If we look at it again, it reads as Pt equals to gamma mc in SI units, or just gamma m in relativistic units, where c is equal to 1 and velocities are written as betas. Let us expand this expression in a Taylor series. The square root can be approximated for small velocities as gamma mc equals to mc times 1 minus negative 1/2 of beta squared, which is approximately mc plus 1/2 of v squared times c over c squared. Now let me multiply everything by c, and we get that gamma mc squared is equals to mc squared plus 1/2 of mv squared. This first term is the rest energy, the energy of the particle at rest, that is due to its mass. The second term is the classical kinetic energy. So for small velocities in the Newtonian regime, in a collision that preserves the mass, the conservation of Pt implies the conservation of kinetic energy. So we can define the time component of the relativistic momentum as the energy of the particle. We will write E equal to Ptc equal to gamma mc squared, or Pt equal to E over C. E is the total energy of the particle, which contains the rest energy and its kinetic energy. From here we can define the kinetic energy as the total energy minus the rest energy. So K equal to E minus mc squared equal to mc squared gamma minus 1. Which for small velocities recovers the classical term of 1/2 mv squared. In classical physics we had two laws of conservation, one for the energy and another for the linear momentum. In relativity, we just need one law of conservation, the law of conservation of form momentum, or in some places written as energy momentum. Here, energy and momentum are intertwined, are part of the same concept. An interesting aspect of the conservation of the time component is that the total pt is conserved, but not necessarily the total mass or the total kinetic energy. The combination is conserved, but we can have a system where the mass transforms in kinetic energy. For example, a radioactive atom that is at rest and emits an electron, and both the ion and the electron gain kinetic energy, which was zero for the initial atom at rest. So we see that the famous equation of the t-shirts, E equals to mc squared, is only valid at rest. The general expression is E equals to gamma mc squared. So if we were talking about space and time as just different aspects of the same space-time, now we see that energy and momentum are but different manifestations of the same form momentum vector. If you want to only write the space components of the momentum, that will be written as p vector equal to gamma mu vector. But this is just part of the total form momentum.